Yeah, this will be a fairy tale about tales from, new tales of wireless input devices. Please welcome Matthias Deeg.
Yeah, good evening everybody. My name is Matthias and in the next couple of minutes I want to tell some new tales about wireless input devices. My colleague and I have collected over the last 3 years. Yeah, so as I said, I'm Matthias and I'm interested in IT security stuff. And this is my colleague Gerhard Klostermeier, with whom I conducted this research project. The agenda for our talk is as follows. At first I want to give a very brief introduction about the used technology, mention some previous work of other researchers, give a short overview of our research, talk a little bit about the attack surface and attack scenarios related to wireless input devices. Then, of course, I want to present found security vulnerabilities of our research. And yeah, I've also sacrificed some stuff to the demo gods today, so I will try some live demos, and I have also one demo on a video. I also have brought 2 interesting anecdotes regarding wireless input devices I want to present at the end, and of course there will be the conclusion and recommendation for you. And hopefully there will also be some time for question and answers at the end. So when I will be talking about wireless input devices today, I will talk about wireless keyboards, wireless mice, wireless presenters, as you can see here. And I will only talk in the slides about non-Bluetooth wireless input devices using proprietary 2.4 gigahertz communication. And as you can see here, usually these devices consist of the input device itself and a specific USB receiver dongle that is connected to the computer device. And you usually have bidirectional radio communication there. So on this slide you can see the devices I have used for analysis purposes and also for proof of concept attacks. So on the left you can see a type of software-defined radio, a popular one, the Hacker F1 by Great Scott Gadgets. And this is actually one I've used mostly in this research. And on the right you can see a USB transceiver dongle. It's a Crazy Radio PA. It is actually used for remotely controlling quadrocopters, but you can also use it for attacking wireless input devices using a specific kind of 2.4 gigahertz communication. The Crazy Radio PA uses a Nordic Semiconductor NF24 2.4 gigahertz transceiver, which can also be used to emulate other kinds of 2.4 gigahertz transceivers. So it's a rather versatile tool, and I will also use it in the live demos. So here's an example of such a USB dongle. Okay, on this slide you can see previous work of other researchers. Our research was inspired by and is actually based on. So attacking wireless input devices like wireless keyboards and presenters is not new. It has been done in the past. For instance, 2010, Max Moser and Thorsten Schröder showed attacks using their Kikeriki hardware attack tool. Also in 2010, there has been demonstrated an attack against the wireless presenter by Niels Teusing. And as you can see, there has been many other research in the last couple of years, also including research by me and my colleague, for instance in 2016 of mice and keyboards, where we have attacked AES encrypted keyboards. And I also have some new information regarding this research from 3 years ago. So yeah, this research project I'm talking about now is a follow-up project to our previous research called Of Mice and Keyboards. And we wanted to find some answers to still open questions. And we also wanted to set the focus of our research on another kind of wireless input device that is widespread, namely wireless presenters. So the kind of device, I have also some here, maybe every one of you is familiar with, this type of wireless presenter, for instance, that you can find in many meeting rooms, conference rooms, at IT fairs or other fairs, that is used everywhere, or mostly everywhere, where people are giving presentations. So here's a short recap concerning our research from 2016. And as you can see, there are some question marks in the result table. And at the end of this talk, there won't be any questions mark left. So I will have new information regarding this Fujitsu wireless keyboard set, the LX901. And here also this question mark disappeared. I can tell you right now, here's an X. So keystroke injection against this Microsoft wireless desktop 2000 keyboard doesn't work. But the interesting row will be this one here to see if different kind of attacks actually also work against the Fujitsu LX901. Here you can see the 12 devices we have tested in total. 3 of those devices are so-called wireless desktop sets consisting of a keyboard and a mouse. So we have the Fujitsu LX901, we have the Fujitsu LX390, and we have the Cherry B Unlimited 3.0. All the other devices are wireless input devices, or also known as wireless presentation clickers, and we also had a look at them to see if they are vulnerable to some kind of attacks we can exploit as attacker. So the test methodology we used is a rather general test methodology I think everybody uses who is doing security analysis of this type of device. So it consists of 3 parts. The first part is the hardware analysis, the second part is the radio-based analysis, and if needed and if possible, we also do a firmware analysis to gather more information. So the first step is all about information gathering to get as much information as possible about these devices we analyze, because all those devices are a black box to us in the first place. So what we usually do is we start with the hardware analysis. We open up the devices, the enclosures of the keyboards, the wireless presenters, the USB dongles. We stare at the PCBs, we try to identify the different chips that are used, or if it's only one chip, then we try to find documentation or data sheets regarding those identified chips, or if also possible, we try to find SDKs, software development kits for those devices, or try to get hands-on development kits, including a development board, if possible, to have the most knowledge possible regarding the chips. It's also interesting to see if there are any test points, for instance, regarding interfaces like I2C or SPI or JTAG that we can use to further analyze the chips or the communication or the configuration of the devices. Sometimes we have to solder some wires and use logic analyzers to analyze data communication between chips if the design allows for this kind of analysis. So as mentioned before, the second step usually is a radio-based analysis. So what we're doing here is we're using the software-defined radio like the Hacker F1 or also other 2.4 GHz transceivers like the Crazy Radio PA with NRF Research firmware developed by Mark Newlin. And we use those devices in combination with different software tools. And the software tool I prefer is the Universal Radio Hacker. And the author of the Universal Radio Hacker is also in the audience today, Johannes Pohl. And it's a really great tool and made it a lot easier analyzing radio protocols, reverse engineering radio protocols you don't have any information about. So if you're interested in software-defined radio and reverse engineering radio protocols, you should definitely have a look at the Universal Radio Hacker. Of course, we sometimes also use other tools like the GNU Radio suite for doing software analysis, and sometimes I also still use Inspectrum for eyeball decoding some recorded signals if I'm not using Universal Radio Hacker from the start, which can do all the steps that are required. And radio-based analysis is actually used to see what is transmitted over the air, what is the actual configuration of the device we have, to gather more information. For instance, for devices where we have unmarked chips, or we have chips that are enclosed in epoxy resin, where we have no information about the actual transceiver that is used, Yeah, so it's also for information gathering and for filling knowledge gaps concerning different parameters we have to know in order to do security assessments. And the third step in the test methodology is the firmware analysis. In this research, we didn't do any firmware analysis of non-Bluetooth devices because it was not required, not necessary for achieving our goals we intended to achieve, or it was simply also not possible to extract the firmware from the transceivers or the microcontrollers we had a look at. Yeah, and on this slide you can see a typical wireless presenter. In this case it's a Logitech R700 laser presentation remote. And what a wireless presenter actually is, it's a stripped down keyboard. So it usually has a button for a laser pointer, and then it has some more buttons for common presentation software hotkeys, so that you can easily remotely control your PowerPoint or Keynote software when giving a presentation. And that's actually it. And some buttons can also be mapped to different keys or key codes, for example, in this case, Escape or F5. So this is also possible. And on the next slides, I have some pictures showing the PCBs of different devices we've opened up. So here you can see an Inatec wireless presenter, a 2002 model, which has an interesting form factor because it is a ring you can stick on your finger and then use for demonstration purposes. And this is the presenter I will also attack later on in a live demo, or I'll try to attack live. Yeah, and the most important thing, or the most important part we are interested in, is the microcontroller and or transceiver. So here we only have one chip. It's microcontroller and transceiver in one device. In this case, it's a chip from Beacon. It's a BK2461, for instance. Yeah, and here I have some other slides showing the internals of other wireless presenters. This is, I think one of the most common wireless presenters, the Logitech R400 presenter. This one has an NRF24 transceiver inside. Here we have a Targus wireless presenter also having a NRF24 transceiver inside. And this is an example of a presenter where I still don't know today what transceiver is used and what microcontroller is actually used, because the chips I'm interested in are covered in some kind of epoxy resin, and I only have this one device to play around with, so I didn't want to destroy it. What I already did is I did some wiretapping regarding the PCB traces to try to sniff the communication between the microcontroller here on the bottom and the transceiver here on the top. And I was lucky because the traces you can see here, the four traces, are actually SPI communication, so the serial peripheral interface. And with this knowledge, I could get some steps further, but I couldn't complete the security analysis, but I will talk about why in a couple of minutes. Yeah, and here I have an example, not of a wireless presenter, but of a wireless keyboard. In this case, it's the Fujitsu LX390. Here we didn't have to scrape the top layer of the PCB and solder the wires directly to the traces, because here we had some test points, test point 1 to, I don't know, 5, and the first 4 test points were also interesting for us, as we can see in a couple of minutes. So in this table you can see all devices, including the RFIC chips we have identified, and also including the USB IDs, the vendor ID, and PID, if you are interested in blocking those devices after this talk, for instance, regarding your device control software. Another important thing is reading the fine data sheets, if you can access them and find them publicly, because the information contained in data sheets is very valuable, and in my experience you should read data sheets at least twice, sometimes also 3 times, to understand them completely and not missing crucial information that can speed up your analysis. For most of the low-cost 2.4 GHz transceivers we've seen in those devices, the data sheets were publicly available, for instance for the NF24 transceiver by Nordic Semiconductor, and also for the CIRF 6936 by Cypress Semiconductor, because those devices are quite popular also in the hobbyist community for doing different stuff. Then we had different RFICs by the manufacturer Bacon, for instance the BK2423 or the BK2461, and those are almost identical to the NRF24 and its used radio protocol. It's called shock burst and enhanced shock burst, but I say almost identical because they were not perfect clones, but almost perfect clones. But some tools that work for the NRF24 can also be used for the Bacon devices, which is very convenient. And regarding one chip that is labeled HS304, we couldn't find any publicly available data sheets, but Mark Newlin, independently of us, also did some research regarding wireless presentation clickers and already reverse engineered some of the information regarding this device, and luckily for us published it in April this year. So we could also use the information regarding this kind of unknown 2.4 wireless transceiver. So on this slide I have an example of the Universal Radio Hacker software tool, which I've used for analyzing the protocols of some of the devices. You cannot see that much on the screenshot actually because the screen resolution was too high, but I can at least tell you it's a really cool tool. What you can do is you can record your signals using a software-defined radio. Then your first phase is the interpretation phase, where you try to make sense of all the bits and bytes, and convert this in your analysis phase. And then in the analysis phase you can annotate all the different ones and zeros like I have done here, and make sense of the complete packet you've seen over the air. And in a next step, if you're confident that you've identified everything correctly, you can try to generate your own packets. So not only replaying packets you've captured, but also try to manipulate captured packets and to see if you can trigger a different behavior regarding the computer system the receiver dongle is attached to. And all those features are implemented in the Universal Radio Hacker software tool. And next I want to talk about the challenges regarding the analysis of wireless protocols in general, and also regarding the wireless protocols we had to deal with in the wireless input devices. So the main challenge is to get from energy that is transmitted from one device to another to maybe an exploitable security vulnerability. The image you can see here is a demodulated signal, in this case of the in-attack wireless presenter I will attack afterwards. In this case, this transceiver uses FSK modulation. FSK is frequency shift keying. Other types of modulation are ASK, so amplitude shift keying, and also PSK for phase shift keying, but I won't go into details here. What's important is you have to identify the modulation first, of course, of your radio signal you're analyzing, and the transmitted energy actually. And if you can demodulate it correctly, you will hopefully get some kind of bit stream. And then the challenge is to understand a sequence of 1 and zeros and make sense, hopefully, of every bit to eventually achieve something like what you can see in this notepad screenshot below. In this case, it's a keystroke injection attack. So my main goal was to analyze the radio communication of all the wireless presenters and also the keyboards, and try to achieve a keystroke injection attack where I'm able to inject arbitrary keystrokes. So not only the page up or page down you have on typical wireless presenters, but to see if I can also inject a small a or a small b or stuff like that, which can be useful for me as an attacker to remotely control a computer system. And here's a summary actually of the challenges that you face when doing reverse engineering of proprietary protocols. So at first you have to find out the signal modulation, then you have to find out the actual packet format, also called framing of the packets. Then it's important to know what fields are actually used in this packet. Then you have to find out what bit and byte order is used, because there are all types of combinations in proprietary protocols you can face. Then you have to identify use checksums. Checksums also, or checksums concerning the transceiver and the radio packet, and also checksums that are in the payload, maybe. So oftentimes there's not only one checksum you have to identify, but two checksums to make sense of a complete packet. And there are also also different kinds of checksums, so additive checksums using exclusive OR or the classic CRCs. And as most of you know, CRCs can be configured in different ways. So if you have a CRC 16, you have to find out the polynomial, for instance. You have to find out the initial value. You have to find out if there is an XOR operation performed and what was the XOR value. You have to find out if there is any reflection done, so if the bit order is converted, if only the bit order of the input is converted, or if also the bit order of the output is converted. So you have or you may have a huge search space regarding those parameters only concerning one checksum. So sometimes brute force is the way we go in this case to try to find out what a possible configuration may be. Yeah, and you of course also have to find the payload contents and make sense of the payload. And another challenge is finding out the use of the radio frequency spectrum. So for instance, frequency hopping. Most of the devices not only stay on one frequency and you can analyze it there, but you have to follow a channel hopping sequence, which makes it much, much harder for analysis purposes and also for attacking purposes. And a last challenge, and which can also be a showstopper, is so-called data whitening or data scrambling, or sometimes also called pseudo-noise, because this is most of the time some proprietary algorithm that is applied to the data before it gets transmitted over the air via electromagnetic waves. And if you don't know the data whitening algorithm or cannot deduce it from recorded signals, you're lost and you cannot continue. And I have still one device where I cannot continue right now because I don't know the proprietary data scrambling algorithm in use. Yeah, and on this slide you can see a typical packet format, which you will find in most of the data sheets as a generic structure. What you usually have is some kind of preamble. You have another field for a sync word. Then sometimes you have an address, control word maybe for retransmission purposes or for defining payload length. Then you have the actual payload of your transmitted packet and a checksum. Yeah, and not all of those fields are used by all the 2.4 gigahertz transceivers I had a look at. So, and on this slide, you can see an actual bit stream, an actual packet of the Inatec Wireless Presenter 2002. And yeah, what you can see here is the configuration that is used, because most of those 2.4 gigahertz transceivers not only have one configuration, but they have many possibilities to configure them. So you can configure the length of the preamble. You can have a 1 byte preamble, 2 byte preamble, a 4 byte preamble. You can have a different length of addresses, for instance. You can have, of course, different length of payloads. You can activate automatic acknowledgements and automatic retransmissions or disable it. So there are a lot of options you also have to find out when reverse engineering those stuff. And of course you have to also identify the parameters for checksums like the CRC16 in this example. Okay, then what's the actual attack surface and what are possible attack scenarios? So yeah, two attack scenarios are your attacker has physical access to those devices, or your attacker is only attacking over the air using radio communication. So it depends on your threat model, which of those attacks are actually important to you. And if an attacker has physical access to your wireless input device, he may have different opportunities or different vulnerabilities he can exploit. Maybe he can extract your firmware and steal your intellectual property, which may be an issue if you're a vendor. He can manipulate your firmware, for instance, change cryptographic key material if there is any, or implant some kind of code that will insert keystrokes when you're currently not using the device, for malware injection. And I already said you can also manipulate cryptographic keys or extract cryptographic keys. But for the wireless input devices, this was not an issue concerning the keyboards we've analyzed. This was an issue for some of the keyboards. The more interesting attack vector actually is attacking via radio signals. So here an attacker may be able to exploit unencrypted and unauthentic radio communication. He may be able to perform simple replay attacks. He may be able to perform keystroke injection attacks. Or he may be able to decrypt encrypted data communication. And the vulnerabilities we have found in our research are the following three. We found unencrypted and unauthenticated data communication. We found missing protection against replay attacks. And we found cryptographic issues which allowed for two different kinds of attacks. So the first attack I want to talk about is mouse spoofing attacks. We've already presented this 3 years ago. And I talk about mouse spoofing because some of the wireless presenters also had support for mouse features. So you not only had a stripped down keyboard with four buttons, you also had a little joystick and you could move the cursor on your target system, and you could also perform left and right mouse clicks, for instance. And if the data communication is unencrypted and unauthenticated and you know the packet format, you can perform so-called mouse spoofing attacks. So as an attacker, you can move the mouse cursor and perform mouse clicks. And 3 years ago, I've demonstrated this with Microsoft wireless desktop set, which was also vulnerable to this kind of attacks. And you can find a video online. What I did there is I attacked the Windows system, opened the on-screen keyboard, and then using some heuristics concerning the screen resolution, for instance, and also the keyboard layout, if it's German or English, I was able, via mouse actions, mouse movements and mouse clicks, to actually execute a simple download and execute PowerShell attack vector. And the result was that you can download and execute arbitrary code on a computer system that's unlocked via spoofed mouse actions. So in the references of the slide, you can see the URL of the YouTube video, so I won't show this again today. Another kind of attack are simple replay attacks, which are the easiest one to perform actually. And all of the wireless presenters we have tested are vulnerable to replay attacks. But replay attacks are not very interesting regarding wireless input devices because there are no security-sensitive inputs you can replay. You can replay a page down and a page up or an escape. But you can only annoy someone that's giving a presentation at a conference, for instance, or at a fair. But it's not very security-sensitive in this aspect. So the more interesting, or the most interesting attack vector for me is keystroke injection attacks. And if this works, an attacker may be able to remotely taking control over a remote computer system. And as I've mentioned before, the data communication of all the wireless presenters was unencrypted and unauthenticated, disregarding data whitening in this case. And by knowing the correct packet format, keystrokes controlled by the attacker can be sent to the corresponding USB receiver dongle. And if there is no input validation on the receiver side, for instance, using a whitelist, it may be possible to actually inject arbitrary keystrokes and trigger those keystrokes on the connected computer system. And regarding our research, only 2 of the 11, I think, devices we've tested were not vulnerable to this kind of keystroke injection attack. So most of the wireless presenters are actually vulnerable to keystroke injection attacks, and you can remotely control the computer system where the USB dongle is connected with. So, and I also had a look again at the Fujitsu wireless keyboard, the LX901. This keyboard uses AES encryption for protecting the keyboard communication. And yeah, the AES encryption had a packet size with a payload of 16 bytes. And the cryptographic issues we found in other keyboards like the Cherubi Unlimited or the Logitech or the Perix from 3 years ago, we couldn't find them in this keyboard. So here's a short recap what we found in those other devices. There was a security issue regarding the implementation of the AES counter mode. And what you could do as an attacker is you had access to all the information marked in red on this slide. And by knowing the plain text of a key release packet and being able to identify a key release packet, you were able to take this packet and modify single bits of those packets without knowing the actual AES key, and then perform a keystroke injection attack. So if you're more interested in this, you can just have a look at the documentation from 2016, and there's also a YouTube video showing this kind of attack against one of the vulnerable devices. But regarding the Fujitsu LX901, we found out that there weren't any issues regarding AES encryption, but by sending simply unencrypted keystroke packets, as described in the official Cypress reference design kit, we were able to perform keystroke injections, because the receiver dongle also accepted unencrypted data communication that we've sent to the USB dongle. Yeah. And we were also lucky because the two-chip design of the Fujitsu keyboard, you can see here, also allowed for spy sniffing, so we could actually see what was the microcontroller sending to the transceiver for performing a keystroke injection attack using our own tools. And the tool I have used, you can see here, and I will also use it later on in a live demo. This is a do-it-yourself multi-protocol TX module. And there's also open source software you can find on GitHub regarding this multi-protocol tool, and this is used for remotely controlling toys like quadrocopter or cars. And there's a community reverse engineering also proprietary protocols by different toy manufacturers for RC controlled toys, and then emulating those protocols on this kind of device. So this device actually has 4 transceivers under its shield. It's a Cypress 6936, a CC2500 by Texas Instruments, an A7105, and an NRF24. So it's a rather versatile tool. And I use this tool because I couldn't find any publicly documented information about the data whitening that is used by Cypress. So what I did some spy sniffing. Also sniffed the configuration of the transceiver of this keyboard, and then simply configured my own Cypress 6936 transceiver with the same configuration, and then tried to get a working keystroke injection attack against the dongle. And I actually was successful. And all I had to do is reading carefully the publicly available documentation by Cypress and using some examples that Cypress also provides and modified a little bit. What was also interesting is that the pseudo noise codes you can see here above this array are the recommended ones by Cypress, and the 2 sample devices I had by Fujitsu also used one of those values. So I assume that the implementation that is used in the Fujitsu devices are regarding the recommendations by Cypress, and all use these initial values for the pseudo noise codes, and then you just have to try which of those 8 initial values works for my device, and then you can perform a simple keystroke injection attack. And here you can see examples of valid payloads, for example 2-byte payload for a small letter A, and here a 3-byte payload for a capital letter A, and here's a capital letter B. And I could find out this information also reading the reference design kit manual, and I also had this information by analyzing the SPI communication between the microcontroller and the transceiver. Yeah, and I also had a look at another secure keyboard, because after releasing the information about the Fujitsu LX901 in spring this year, I was asked about another Fujitsu keyboard, the LX390. So I also had a look in this wireless input device, and it was also advertised with secure 2.4 gigahertz technology, so it was interesting for me, but AES encryption was nowhere mentioned in this case. But it was marketed as secure, so we had a closer look. So, and here's a small quiz. Here's an old data sheet, or an excerpt of an old data sheet and a new data sheet. Can you spot a difference? Yes, I think I've heard the correct answer. This keyboard is no more secure. Yeah, so here you can see the PCB of this device we've seen previously. It was actually a SPI interface. I was able to analyze the SPI communication, and by this checking the SPI communication against available data sheets I had, and I found out that the communication looked like the communication found in the LT8900 based RFIC controllers. And with this knowledge, I was able also to capture the configuration of this device and properly decode some stuff. So here's another example of an actually captured packet, what it looks like. And now here's the interesting part, because this device uses data scrambling or data whitening. But what was interesting is that the same plain text resulted in the same ciphertext for two different sample devices. And that's always good to have, so no device-specific cryptographic key in this case. But what was also interesting is I had different checksums for the same payload. And this is because this kind of device allows for different initialization values when configuring the device. And the two sample keyboards I had different CRC initial values, but they didn't have different seed values for the data whitening algorithm. And this helped me in performing an actual attack. So the same data scrambling is used by different devices. By this I could extract a kind of key stream by only analyzing one device. And as you can also see here, there is no kind of message authentication code involved, so unauthenticated communication. And thus I perform the known plaintext attack, because I know the known plaintext due to SPI sniffing, and then I can try to correlate the plaintext communication with the whitened communication I've captured over the air, and then I get a key stream. And I could also figure out the CRC parameters for a CRC calculation. I think, in this case it was a pretty standard configuration. I only had to find out the 1 byte initial value. For my device, I could simply use the SPI sniffing tool. If you want to perform an actual attack against a foreign keyboard, you have to do some brute force attack. So you have to capture some messages and then try to find out which of the 256 possibilities works. And if you have this initial value for CRC, you can perform a data sniffing attack, and as I will show in a couple of minutes. So the Fujitsu LX390 keyboard is affected by the following 3 vulnerabilities. There is missing protection against replay attacks. There is a missing encryption of sensitive data. So there's only data whitening use, but all the keyboards are using the same data whitening. So if you have analyzed one, you can decrypt actually the communication transmitted by all the other keyboards. And there's insufficient verification of data authenticity, so no message authentication code. So you can perform replay attacks, keystroke sniffing attacks, and keystroke injection attacks. And I think I haven't mentioned why replay attacks are interesting. Replay attacks can be used to replay the entry of a password when unlocking a device. So, for instance, if you're in the same room with your victim and your victim is coming back from a coffee break and logs into his computer again, you just press the record button when he's entering his password and unlocking his PC, and when he goes to the next coffee break, he will screen lock his computer. Then you go to his computer, press the play button for the playback attack, and you can unlock his PC. So replay attacks are also a thing you have to consider. And this is the open challenge I still have, the Kensington presenter. I can sniff the spy communication between the microcontroller and the transceiver, which are unknown because they are under epoxy resin. I assume that is also an LT8900 based RFIC device, but I don't know for sure. And data scrambling algorithm works differently than for the Fujitsu keyboard. So this method didn't work, and I also tried with some PL1167s, which are claimed to be compatible with this LT8900, but I also wasn't successful in this case. So now it's time for some live demos, and I have four, and three of them I tried to show live, and then I also have something related to Bluetooth research we also did last year, if we have time. So the first attack is old news are so exciting, attacking a wireless presenter. So what I will try to attack is this in-attack wireless presenter we've seen previously. So now I have to insert the correct USB dongle. Now I have a cheap picture-in-picture solution here with the Lifehack camera. And here I have this wireless presenter in this ring form factor. And as you can see, I can press page down, page up. And what I will try now is using the Crazy Radio PA as an attack tool. And I've prepared this. What you can see here is the key checker tool. It's open source, already available on GitHub, which I will use to perform this keystroke injection attack. It supports different protocols. So here I have to say I want to attack an in-attack VP2002, and I will also give it the specific address I have to sniff previously, but I also only want to attack my own devices. So now let's see if something happens here. And as you can see, something happens. So a command shell opened up, and also a calculator, because you cannot have a code execution exploit without opening up the calculator. So this was the first example, keystroke injection attack against the wireless presenter. Okay, so then I have another example. So this time using another kind of device, namely the 4-in-1 multi-protocol device. I try to show it to you here. So this is the actually device with different transceivers, and this is only the power supply I have here in my other hand. And now let's see if I power up this device. Hopefully something will also happen. And as you can see here, also a command shell opens up and enters some keys. I haven't implemented any error handling in this device, so you can see one L is, for instance, missing right now, because there's no retransmission if the packet was not acknowledged by the receiver in this case. But it's just for proof of concept purposes. And it worked fine. So, and the last live demo I want to show is regarding sniffing. This is also only in a proof of concept stage right now. So what I have here is the Fujitsu LX390 keyboard. Now I have to find the correct dongle. I hope it's this one. And I will open a notepad so that you can see that something is happening. Now I will start, now focus. Okay, so the autofocus doesn't work, right? No. Let's see again. Okay, it's refocusing. Now some white. Okay. Maybe it refocuses if I enter some stuff. So I will start my sniffer here. Now I will insert the dongle, and let's see. Oh, I've mistyped something, but what you can see is you can actually capture the keystrokes and decrypt them. And this keyboard uses the data whitening algorithm, and all the keyboards of this model are using the same data whitening. Okay. No. Then I also have a fourth live demo, but I think I don't have enough time, or okay, I will show this. It's a video, so it's not live. And this one shows another kind of attack vector regarding Bluetooth devices, because my colleague and I also did some Bluetooth research in 2018, and we found, I'll put it here. We made two interesting observations. I will skip some stuff. So here you can see the interesting observations. So the first observation was cryptographic key material of bonded Bluetooth devices can be extracted by an attacker rather easily with physical access. So that's an attack requiring physical access. And yeah, most of the Bluetooth stacks of modern operating systems, so in this case it's the Bluetooth stacks of Apple iOS, Apple macOS, and Android devices, do not strictly bind specific properties of a bonded Bluetooth device with its pairing information. And what this means is demonstrated in this video here. So here we have an Android phone on the left as the computer system we are targeting, and on the right we have Bluetooth headphones. These are Bluetooth classic headphones, and these headphones are connected to our Android device. And with physical access to all the Bluetooth devices, the Bluetooth peripheral devices we've tested, we were able to extract the firmware and also the cryptographic keys. So in a couple of minutes, if you have physical access, you can open up the device and then try to extract the cryptographic key material. So here you have to unscrew 3 screws, then you can open up the device, have access to the PCB. And what is used in this device is a Qualcomm Bluetooth audio platform, yes, and also an external SPI flash memory chip. And all the interesting data is on this serial flash memory chip without any protection. So if you have physical access, you can simply extract this information from this device rather easily. And this is not only true for peripheral devices like headphones, but also for keyboards. Yeah, and you can do different kinds of extraction. You can either do an off-chip extraction, so unsoldering the chip and doing this way, or you can use this device shown in the video here. It's a pogo pin adapter, and if you have a steady hand, you can also do it on chip. Then you use the software tool of the universal programmer you're using, and you're able to extract the firmware. And not only the firmware, but also the current configuration of your peripheral Bluetooth device. And somewhere in your extracted dump, you can also find the Bluetooth address of the connected device and the Bluetooth address of your device itself, and the shared secret between those two devices, making up the trust relationship. So it's called link key in Bluetooth Classic in this case. So what you can see here on the left is our attacker system, and on the right we have our victim system. The test setup concerning this Android device was that the headphones were connected or bonded with the Android phone, and I think the headphones were also configured as a so-called trusted device. So the headphones were able to unlock the Android phone if it was screen locked in this scenario. So this is what's shown here. That's the so-called smart lock feature, I think supported since Android 7 or 8. I don't know actually. So, and what the attacker now does, he configures his own attacker device with the extracted Bluetooth information, so the Bluetooth addresses and the extracted link key. And then he can, for instance, emulate a keyboard. So you extract information from headphones, and then pretend to be a keyboard. And now, interestingly, your Android phone doesn't care. So you can perform keystroke injections then, because it thinks, hey, I have a trust relationship between you and me, and I don't care if you have been headphones before and now you're a keyboard. So this was interesting for us also. Okay, how many minutes do I have left? Okay, I have two also somewhat interesting and also funny anecdotes. 2016 we've published security vulnerabilities regarding the Cherry keyboard named B-Unlimited AES, and Cherry rebranded and re-released this keyboard under a different name with a different case. So they have just re-released this keyboard as B-Unlimited 3.0. But it uses the same 180-bit AES encryption with the same security issues. And not all people buying this Cherry wireless desktop set knew this, because one of our customers bought the B-Unlimited 3.0, and during a security awareness event of one of my colleagues, who also showed this attack during a live hacking demo, he was asked after the presentation if the B-Unlimited 3.0 is also affected. And then he said, oh yes. And what our customer has done, he has already ordered keyboards for all the locations in Germany by a device which was known to be having security issues, but he didn't get the memo in this case. So this was also interesting. Yeah, another interesting thing was when I had a closer look at a current B-Unlimited 3.0 in spring this year. I wanted to look up the FCC ID for gathering some information, and I found out that the FCC ID printed on the device, which you have to have if the device is sold in the US, was not valid. So there was an issue in production that a wrong FCC ID was printed on all the devices that have been sold. Another interesting anecdote or story is real and fake devices. Because in the last 3 years, we've bought different Logitech R400 devices via Amazon, also for some colleagues and security awareness trainings. And we've bought 3 devices recently at the beginning of this year and got 3 different devices delivered. So when we've opened it up, when we tried to perform the keystroke injection attack I've showed you a couple of minutes ago, we only succeeded with one of the devices and not with the other 2. And then we thought, hey, what's going on? Have they patched a security issue, or what's different between those devices? Then we've opened them up and saw that actually the hardware layout is different. So number 1, this was the device where the keystroke injection worked. This was device number 2. So here we had unmarked chips, a 2-chip design, and here was number 3. We had a single unmarked chip, but definitely different from this device, which I think is an original one. But until today, I don't know if the other devices are actually counterfeit devices, fake devices, or if they are actually Logitech devices, just of a different kind. And Logitech also couldn't help us in this case. They replied to me that all internal information regarding parts and so forth are copyright protected information of Logitech and cannot be provided. And the first thing they told me when I asked the question is that if I open up the device, my guarantee is void. So I told them that's the least issue I have right now, because I have probably some bad USB devices I'm using in my company, and I want to know, is it a fake device, a counterfeit device, or is it an original one? But until now, I don't know actually. So the conclusion, different security vulnerabilities lead to different kinds of attacks. So if you have unencrypted and unauthenticated data communication, you may have, or you have mouse spoofing attacks, keystroke injection attacks, or keystroke sniffing attacks. Missing protection against replay attacks allows for replay attacks, obviously, and cryptographic issues allow for keystroke injection attacks and also keystroke sniffing attacks in some cases, like with the Fujitsu keyboard and the data whitening algorithm used. So in this table you can see the summary of our research regarding the wireless presenters. So we had two devices that were not affected by keystroke injection attacks. The Kensington is still an open question if it's possible not to perform keystroke injection. And as mentioned before, Mark Newlin also did some independent research and published it in April this year. He had a look at different wireless input devices that are available in the US. And yeah, he also found out that most of them are vulnerable to keystroke injection vulnerabilities. And here you can see the updated table I've shown in the beginning. And yeah, what I can say is the insufficient protection of code and data when having physical access is not there regarding the LX901, so we were not able to extract the firmware and the cryptographic key that is used, the AES key, but we were able to perform mouse spoofing, replay, and also keystroke injection attacks. And as also mentioned before, keystroke injection attacks did not work against Microsoft Wireless Desktop 2000. Yeah, and another conclusion I can draw is that security vulnerabilities may also be re-implemented in new product versions, because the Logitech Alpha 100 is a good example for this. In 2010, there was a security issue reported in the Cypress RF-based version by Niels Teusing. I've mentioned in the beginning in the previous research. Then we have reported a security issue back in 2016 concerning the NRF-based version. So they did a product update and also used a different transceiver, but re-implemented the keystroke injection vulnerability in some kind. And yeah, if you bought this device in the beginning of 2019, you still got a vulnerable version. So here are my recommendations concerning wireless input devices. Yeah, choose your devices wisely is one recommendation. Do not use wireless desktop sets with known security vulnerabilities in environments with higher security demands. So some of those devices may be fine for using at home, but yeah, in a business context, I would not recommend using them. What our research also showed concerning Bluetooth and non-Bluetooth devices is that we currently consider Bluetooth wireless input devices more secure than non-Bluetooth devices at the moment. Yeah, because in most of the devices using proprietary 2.4 gigahertz radio communication, there were security issues. But there are also now different models that have been released in the last couple of months that have fixed the security issues we've reported, so you can also get some wireless desktop sets, wireless keyboards, wireless mice, and also wireless presenters that are not affected by keystroke injection or replay attacks anymore. For instance, Logitech offers you to replace or update, depending on the device, your vulnerable devices. And yeah, if you're still in doubt, use wired input devices. And yeah, there are also some new interesting software tools that have been released this year. One is by Mark Newlin, the wireless presentation clickers. It's available on GitHub. Another interesting research concerning different projects was performed by Markus Mengs, who has found new security vulnerabilities in the Logitech unifying receivers and did research he named Logitecher and Munifying. And what we have done is we have forked Mark Newlin's presentation clickers and included our research results in his repository, ported the tool to Python 3 and called it Keyjector. That's a tool I've used previously for the live demo. Yeah, and one more and last thing, barcode scanners are also just keyboards with a different form factor. And this example here is also vulnerable for keystroke injection attacks. It's also using a proprietary 2.4 gigahertz communication protocol. It uses a Bacon chip, a different one in this case, 2535, has a more complicated communication protocol. I haven't understood completely yet, but I understood it enough to perform a keystroke injection attack. And today I have released a security advisory you can see here. So thank you very much. That's it.
Thanks, and thanks to you for allowing the overtime and paying respect to the demo gods for the live demo. Since this is the last talk for today, we still have time for questions. So if you do have questions, please.
Is there, at least at the most used operating systems, some way how to use these devices safely, like to bind them with the exact process limit or the filter, the keystrokes only to some wide listed and so on, or just only ways to throw it away?
There is a way regarding Linux where you can whitelist different scan codes. But all those devices, or actually the USB dongles, are identified as simple HID, human interface device. And there is no whitelisting in most of the operating systems built in. But for Linux, there is a patch, I think also provided or published by Logitech for their devices, which you can apply. And then if you're inserting a Logitech USB dongle, this whitelisting filter will be applied to this specific human interface device with a specific vendor and product ID. So there's a possibility. But yeah, regarding on the other operating systems, it's not built in. And there's no capability of updating this device. Yeah, it's the whitelisting of keystrokes or scan codes. It's, yes. Keyboards should have all the keys. That's right, yeah. So you cannot differentiate if the original keyboard is sending you the radio packet or if an attacker is sending you the radio packet. Because if there is no message authentication done in any way, you just cannot differentiate this.
Yes, but is there the way, at least at Linux, how I can bind this particular keyboard only for that presentation software, for example?
Okay.
And not for terminal, for running anything.
Okay, so I'm not aware of this kind of configuration possibilities, at least regarding the popular operating systems, Windows 10 and Linux and Mac OS 10.
Further questions? Nope. Everyone's happy? Well then, thank you very much again.
Thank you very much.